All right. So, as according to the schedule, this week we are going to talk about light, and specifically we're going to talk about how light energy is transmitted into some kind of another type of energy that we'll call electric energy. So our first question, how is light absorbed? How is light absorbed? And so you probably can think of an organism or several that can actually harness sunlight in order to accomplish a task, and that's the task of building sugars and producing oxygen. And what are those organisms? Plants. And so what I want to tell you is no matter what the material is, everything can absorb light, and everything does absorb light. And at the atomic level, the same thing happens in virtually all organisms when they absorb light. The thing that's different about plants is when something happens, sometimes it can absorb just the right amount of energy to completely break something free. All right? So we'll kind of put this into context of what goes on in living organisms. Yeah, so plants absorb light energy and convert it into chemical energy. And so this is something we can't do. We absorb light energy, right? What happens when we absorb light energy? If you sit out in the sun for a long time, what happens when you absorb light energy?
You get burned.
You get sunburned, right? So you're absorbing light energy as well, but you're not harnessing it to generate chemical energy like a plant is. So we need to talk about exactly what's going on. Well, what happens is regardless of what the material is, the electrons in that material absorb the light. So when light hits a material, some of that light hits an atom just right to where an electron, bless you, can absorb that energy and then basically get excited. As that electron absorbs energy, it gets itself further away from the nucleus of the atom. And so, again, this causes electrons to jump to a higher energy level. And this happens in all materials. In all materials. As they absorb light, this is what happens. Electrons get excited and jump to a higher energy level. That is, they get further away from the nucleus of the atom. So if you were to look at an atom, it would look basically like this. Here in the center, you would have the nucleus. And then surrounding that nucleus, you would have electrons. And so at various places in the area surrounding, or really in the volume, the space surrounding that nucleus, you'll have electrons. And so as these electrons absorb light, what they do is they get excited. So if we've got light that comes in here, so this is light, what it does is it excites this electron and sends it up to a higher energy level further away from the nucleus. That happens in all materials. Happens in our cells, happens in plant cells. But what plants do is some of these electrons, the amount that they jump up is just right, and they can be completely passed away from that atom onto something else. And why is this important? Why is it important to know that the electrons can be transferred in plant tissues? Last week we talked about current, right? And we talked about current is the movement of what? And in terms of electricity, it's a movement of electrons. So when electrons start moving, you've got a power source, right? And you've got power that's on the move. And as electrons move, you can harness that energy, and that's what plants do. And so in our cells, these electrons don't get passed on to other molecules and start moving. They just fall back down and release light. They fall back down to where they were originally, and they release light. And the nice thing about this is the amount of light they release the type of light they release should be equivalent to the light that they absorbed, right? The amount of energy that they absorb to jump up to a higher energy level should be equal to the amount of energy they release when they drop back down to where they started. And so what's cool about this is you can predict what kind of light a material is going to release by how the electrons behave. And this is how you can make lights that are blue and lights that are orange and lights that are pink and lights that are green, because the electrons behave in very specific ways and release very specific types of light. All right? Sound good? All right. Any questions about that? So how is light absorbed? It's absorbed by the electrons. And so here's what that looks like. Here you can see up in the top diagram here that you have that electron at what we would call the low energy level or the first energy level. Light hits it. It excites the electron up to a higher energy level, and that electron basically has, three different options. One is that electron can fall back down. That's what's happening on the left. The electron falls back down and it releases light. Releases basically the same energy light that it absorbed. It can also release it as heat, but usually releases it as light. Or that electron can be completely transferred to a different molecule, and now you've got an electron on the move. And electrons on the move provide energy that can be harnessed. And then the one over on the right is that electron can drop back down and release light to a neighboring pigment molecule that can excite an electron there. And this is how plants kind of play a game of hot potato almost until the light gets to the perfect amount of light to excite the electron just right to where it leaves and gets transferred to another molecule. All right? You might be thinking, like, why are we talking about plants? This is a physics class. But it all has to do with how light behaves. It's a great illustration of how light behaves. So next question that we're going to deal with is this one. How much energy gets released? How much energy gets released? What are we talking about? So when an electron gets excited and then falls back down, how much energy gets released? And it's basically this. The same amount of energy an electron absorbed gets released. Now, it's not perfect. There is some loss, but for our purposes, we're going to assume a perfect transition. And even in nature, it's pretty close to a perfect transition, that the amount of energy the electron absorbs, it releases. Well, it is always, that always has to be the case, but we're going to deal with it that it releases 100% of it as light, which isn't always going to be the case. Some of it it's going to release as heat, as just raw energy. All right, and here is an equation for telling us the wavelength of the light released. The wavelength of the light released. You remember talking about the relationship between wavelength and frequency of light? I think, did Stephanie do that lesson with you guys? I think that was the day that I couldn't come because one of my kids was sick. But yeah, there's a relationship between the wavelength and the frequency of light. Right? The higher the frequency, the lower the wavelength. The lower the frequency, the higher the wavelength. Right? Well, we have this equation that tells us 1 over the wavelength of light in meters is equal to R times this equation here. 1 over n1 squared minus 1 over n2 squared. And let's talk about what these are. So R is what's called the Rydberg constant. R is the Rydberg constant. It's equal to 1.1 times 10 to the 7th inverse meters. Inverse meters, or meters over 1. Okay, so we've accounted for R. R is a constant. And that makes sense based on how this equation is structured, because R is being multiplied by another factor. N1 and N2 are the energy levels of the electrons. N1 is where it starts. N2 is where it finishes. Okay. N1 is where it starts. N2 is where it finishes. Again, N1 is where it starts, and N2 is where it's finishing. Now, the thing you have to realize is you may do this equation, and you may end up getting a negative number. Is there such thing as a negative wavelength? Right? Wavelength is a distance, right? It's a distance peak to peak or trough to trough, crest to crest, trough to trough, right? So it doesn't make sense to have a negative wavelength, right? So you may end up putting this in such a way that you get a negative number, but just reverse that number. And so what you might want to do is write this equation. You could just put the absolute value signs around the 1 over N1 squared minus 1 over N2 squared. And then that way it eliminates the possibility of getting a negative number. Or you could just, at the end, if you get a negative number, make it positive. And so maybe you could put the absolute value sign around the whole thing, around the R and the rest. Some thick brackets. All right? We okay with this tool? A little bit more complicated algebraically if you're going to solve for energy level. Or even if you're just going to solve for wavelength, it's a little bit more complicated algebraically because wavelength is on the bottom of a fraction. But we can handle it. And so this is one in which it's a little bit complicated concept-wise, and it's a little bit complicated algebraically. But we're towards the end of our experience in this class. Hopefully you're comfortable enough to meet this challenge. We okay? So how much energy gets released? Basically the same amount of energy that the electron absorbs. And we're going to assume it releases all of that energy as light. Okay? And none of it as heat. Is that really what's going to happen? No, but for simplicity's sake, that's what we're going to assume. All right. Ready for some problems? Okay. So if an electron jumps from the first energy level to the fourth energy level when absorbing a photon of light, what wavelength of light will be released when the electron returns to ground state? If it returns to ground state, it's going back to where it came from. Okay. What do we have? What do we have, or what are we given? What do we got, Micah? Give me something.
Energy levels.
Okay, so we have N1 is equal to 1, and N2 is equal to 4, right? N1 is where it started, N2 is where it ends up, and it ends up in the fourth energy level. That's it. That's all this problem gives us. Do you agree? See anything else? It's really just giving us a scenario for everything else. Now, what tools do we have to work with here?
The 1 over wavelength is equal to R times 1 over N1.
Yep, and I'm going to put it in absolute value. 1 over N1 squared minus 1 over N2 squared. Absolute value. Okay? So we have that tool. Yep. We also know what R equals. That's another tool that we have. R is equal to 1.1 times 10 to the 7th inverse meters. Let me get out of your way real quick. Does everybody agree with this? We have these tools. This is what the problem gives us. Now, what do we want? What is the problem asking us for? The wavelength. So we want this. Now we can manipulate this algebraically to solve for this, or we could just solve for 1 over lambda and then invert it. Okay? You could do it either way. I prefer to just solve for 1 over the factor and then invert it. Just do 1 divided by that number. Okay? Instead of that number divided by 1. Okay? We okay doing it that way? Because if you want to solve for lambda, what you would do, right now lambda is being divided away, so you would multiply it to both sides, and you would end up with 1 is equal to R times the absolute value of this times lambda, and then you would divide R times the absolute value away from both sides. And you would end up with lambda equals 1 over R times the absolute value of 1 over N1 squared minus 1 over N2 squared. We could deal with that. Not really super complicated. Okay, But I'm going to do this. I'm just going to say, I'm going to solve this for 1 over lambda, and I'm going to plug in what we know. So R, we know, is a constant. It's 1.1 times 10 to the 7th inverse meters. And then we're going to multiply this by the absolute value of 1 over what is N1. It's one of our things that are given that we know. N1 is 1, so over 1 squared minus 1 over 4 squared. We okay with that so far? So we have 1 over lambda is equal to 1.1 times 10 to the 7th inverse meters multiplied by the absolute value of 1 minus 1 over 16. Okay. We okay there? Okay. 1 minus 1 over 16 is 15 over 16. Do you agree with that? This 1 is 16 over 16. And then so we have 1.1 times 10 to the 7th inverse meters times 15 over 16. And this would equal 1 over lambda. So we get 1 over lambda is equal to 15 divided by 16 times 1.1 times 10 to the 7th power. And if we're going to do it in significant figures, this is 2 significant figures. This is an infinite number of significant figures, but we're going to limit our number to 2 significant figures. Although you could make an argument that since this is a constant, we can assume that it's exactly 1.1, in which case we would limit it by this. But 15 divided by 16, I actually don't know how many significant figures that is. But we'll just present our answer in 2, and we get 1 over lambda is equal to 11. No, sorry, it would be 10 million. That's only going to be 1 significant figure, so I'll do 10,300,000 inverse meters. Everybody okay with that? Anybody want to see this worked out, how I got to that? All right, are we done? No, we don't want 1 over lambda, we want lambda. So we've got to invert this, which means we have to invert this and do 1 divided by this number. And that's good. How do we know we're on the right track algebraically? What's our unit right now? Inverse meters. If you invert inverse meters, what does your unit become? Meters. And why is that good? How do we measure wavelength? In meters. So 1 divided by 10,300,000 is essentially 0.000000 1, 2, 3, 4, 1, 2, 3, 6, 0, 1 meters. 0.00000001 meters, or you could do it as 1 times 10 to the minus 1, 2, 3, 4, 5, 6, 7. 1 times 10 to the minus 7 meters. Okay, and again, this is assuming that all of the energy absorbed by that electron from the light is going to be emitted as light. We okay with this? Incredibly exciting. I know, this is good stuff. Am I okay to erase this? Everybody still writing? Okay. Oh, I could have left those. Could have left the have, tools, and want. All right. Let's put those back. Have, tools, and want. All right. So the next one, what wavelength of light would be required to make an electron jump from the 3rd energy level to the 6th energy level? What wavelength of light would be required to make an electron jump from the 3rd energy level to the 6th? So what do we have? Yeah, we have N1 and N2, just like the last problem gave us. N1 is equal to 3, N2 is equal to 6. Now our numbers are a little bit different, but we're given the same values that we were given in our previous example. Okay, tools, we have the same tools. 1 over lambda is equal to R times the absolute value of 1 over N1 squared minus 1 over N2 squared. And we also have R is equal to 1.1 times 10 to the 7th inverse meters. Okay. So in a lot of ways, this is the same as the previous problem. Be maybe manipulated in a slightly different way. If you wanted to, again, solve for, if you wanted to rearrange your tool to solve for lambda. All right, so what do we want? We want the same thing, right? So again, I will solve for 1 over lambda. Although if you wanted to, you could say, let's actually do this one saying lambda is equal to 1 divided by R times the absolute value of 1 over N1 squared minus 1 over N2 squared. So let's go ahead and manipulate our tool like that, make it a little bit different than the first one. Then it's already set up for us to do that inversion. So lambda is equal to 1 over 1.1 times 10 to the 7th inverse meters times the absolute value of 1 over 3 squared minus 1 over 6 squared. We see that so far? Okay. Now, lambda then is equal to 1 over 1.1 times 10 to the 7th inverse meters times the absolute value of 1 over 9 minus 1 over 36. Oh, absolute value. One over 9 minus 1 over 36. This one's not going to be quite as simple as doing 1 minus something. We'd have to find a common denominator. The common denominator of 9 and 36 happens to be 36. And so this would become 36. How much do you have to multiply 9 by to get it to equal 36? 4. So we got to multiply this by 4. All right. And so now we have lambda is equal to 1 over 1.1 times 10 to the 7th inverse meters multiplied by 3 over 36. You okay with that? 1 divided by 12. Okay. So let's do this. 1 divided by 1.1 Let me do that again. 1 divided by 1.1 E7 Okay. And so again, we'll do it just to 2 significant figures so that we don't get carried away. In this case, I'm going to present our wavelength in scientific notation, but if you wanted to write out a bunch of zeros, you could. So I'm going to present it as 1.1 times 10 to the minus 6 meters. That our wavelength is equal to 1.1 times 10 to the minus 6 meters. Now, our other problem that we did, our wavelength was 1 times 10 to the minus 7 meters. Which one's a longer wavelength? 10 to the minus 7 or 10 to the minus 6? Basically, both of them are pretty much 1 times 10 to the minus something. Which one's a bigger wavelength?
10 to the minus 6.
10 to the minus 6 is a bigger wavelength, which means this light would have lower frequency, which should have lower energy. So this is lower energy light. So which means that the distance from the first to the second energy level is actually a greater amount of energy jump than from the third all the way to the sixth. Wait, no, the other way around. Sorry, because this, yeah, no, that's right. Yeah, this is a bigger wavelength, so it's smaller frequency, less energy. I was right. All right. Cool. Any questions, thoughts, concerns? Is it pretty simple? Pretty simple. Okay. So what I want to do is show you a problem in which you would have a multiple step down. And then that'll allow you to basically have the tools to solve for any of your homework problems. Oh, gosh, I did it again. Let me try this red marker and see if it's any more vibrant than that blue marker. Yeah. Can you guys see okay?
Yeah.
Writing a little bit smaller than I normally do, but I think still plenty big. My vision's not great, so. All right. So I have, let me skip this one. Oh yeah, this is the one here. So the next one, the one I just skipped, was similar to the first two. So I want to show you how you would do this problem, how you would go about setting it up, and we'll be pretty close to done. So what do we have? If an electron released 4 photons of light as it fell from the 5th energy level, what are the wavelengths of each photon? Okay. This is an interesting problem. Because on the surface, it looks like we're gonna do this like we did before, where it gives us N1. N1 is the first energy level, or you could say N1 is actually the 5th because it's falling from the 5th to the 1st. So N1 is 5. N2 is 1. And we're like, okay, well, we'll just go about this the same way we did before. Our tools, we rearranged our tool to say lambda is equal to 1 over r times the absolute value of 1 over n1 squared minus 1 over n2 squared. And r is equal to 1.1 times 10 to the 7th inverse meters. Right, so on the surface, it looks like we're going to solve this problem the same way we have our previous problems. But this problem reads a little bit differently, doesn't it? What is the problem actually asking us for? So on the surface, we want wavelength, right? But we want the wavelength of 4 different photons of light. And so this problem is a little bit different in that if here's our nucleus, and here's our first energy level, and here's our second energy level, and here's our third energy level, and here's our fourth energy level, and here's our 5th energy level, and here's an electron here in the 5th energy level. It's not falling all the way down to the first energy level. If it were, we would just solve it the way we were our other problems. But this is not what's happening. Instead, it's falling down stepwise, 1 energy level at a time, emitting various photons of light. Okay? Okay. So it falls from 5 down to 4, and emits a photon of light. Emits a photon. Okay. Then it falls from 4 down to 3 and emits another photon of light. And then it falls from 3 down to 2 and emits another photon of light. And then finally it falls from 2 down to 1 and emits a photon of light. So it's falling down stepwise, releasing 1 photon every time it falls. And so we actually, in order to solve this problem, we would need to do what we've been doing in the previous problem for every single one of these drops. So for this drop, in 1 is equal to 5. In 1 is equal to 5. In 2 is equal to 4. In this drop, in 1 is equal to 4. In 2 is equal to 3. Right? In this drop, in 1 is equal to 3. In 2 is equal to 2. And then finally, in the last and final drop, in 1 is equal to 2. And in 2 is equal to 1. Right? And so what's really nice about this is you can be asked a single question on your homework and have to do a whole series of problems in order to figure that one homework question out. And that's fun. Those are great questions, right? Great questions. Because what about if alternatively, so does this make sense that this is how we would set up this problem and solve for it? What if you had a question like this? And I said that a photon of light excited an electron from the first energy level to the 5th. Okay, so we have this scenario here. Went from the 1st all the way to the 5th. And I asked you, what are all of the photons of light that could be emitted? What are all the photons of light that could be emitted? Okay. What I want you to do is take a couple of minutes working with those around you. See if you can come up with all of the different, don't actually calculate the wavelengths, just all of the different photons of light that could be emitted as that electron falls back down. All right? Take about 2 minutes, come up with a list of those as you think through them. All right? You're going to work in groups as large or as small as you want. Work by yourself if you want to, or with as many people as you want to. All right? 2 minutes, starting now. Okay. Any ideas? So we had this electron get excited from the first energy level up to the fifth, and you need to determine all of the photons of light that could be emitted in this process. Well, here we've accounted for 4, right? If it fell from the fifth down to the fourth, and then the fourth to the third, and then the third to the second, second to the first. But it could have also fallen from the fifth all the way down to the first, right? And release that photon of light. Right? And then it could have fallen from the fifth down to the third. And just bypass the fourth, releasing this photon of light. And it could have fallen from the fifth down to the second, releasing this photon of light. And so now we've added 3 additional photons of light that could be produced in this scenario where an electron gets excited from the first to the fifth. Okay? 3 additional photons. Is that all of them? What do you think? I feel like there should be more. Yeah, Joshua.
I mean, there's no halves at all?
No, it's got to do whole energy levels. Yeah, that's a good question. But this one here, after it fell from the fifth down to the fourth, it could go from the fourth all the way down to the first. Or it could go from the fourth to the second instead of from the fourth to the third. That's 2 more photons of light. From the fourth down to the first, from the fourth down to the second. So that's 2 more. And then this one here, the third one, instead of dropping to the second, could have dropped all the way from the third to the first. And so that's 3 more photons of light. So which means in a scenario where you excite an electron from the first up to the fifth, there are these 1, 2, 3, 4, 5, 6, 7 photons, plus 3 more. So that's 10 total photons of light that could be emitted. And that's assuming only that all of the energy absorbed is released as light, none of it released as heat. And so this is all done assuming that this atom right here is hydrogen. And I don't know how many of you have had chemistry, but hydrogen has basically 1 proton or 1 neutron in its nucleus, 1 proton in its nucleus. Sometimes has 1 neutron, usually has 0 neutrons, and has 1 electron. But it has 7, the equivalent of 7 energy levels that the electron could be in. It just always sits in the first energy level unless it's excited. So what that means is if you flash light into hydrogen and allow that electron to absorb light and then fall back down, you should see several different colors of light that could be emitted in this process. You could get 10 just from it getting excited from the first up to the fifth. But if it got excited from the first up to the seventh, then you have even more photons that can be produced. And so we call this the emission spectrum of an atom. And have any of you never heard the name Albert Einstein? Everybody's heard the name Albert Einstein? So Albert Einstein won the Nobel Prize, and everybody thinks it's with his work with the nuclear bomb. But he actually didn't. He didn't win the Nobel Prize for that. He won the Nobel Prize for explaining the emission spectrum. That when you shined light into hydrogen and you got a very specific bands of light that came out of it, he explained what was going on. He explained it this way. That's what he won a Nobel Prize for. It's good stuff. All right? So does that make sense? That would be a cruel question to ask if that was in addition to several other questions, because if you had to find the wavelength of every possible photon, not only would you need to figure out all the possible photons, but then you would need to go through this process here using this tool to solve for all of those wavelengths. But what you can anticipate is a problem like this, where it said the electron falls from the fifth to the fourth, emitting 4 photons of light. And so you're noting it's dropping stepwise. And then it says, okay, well, what is the wavelength of each of those photons? And you could also anticipate us bringing in some material from a previous section and to say, okay, what is the energy in that photon of light? Okay. Do you remember that? Let's do one of those problems and then we can be done, okay? All right. So let's take our answer from our second example problem. Okay, here I'm just gonna make up a problem for you. So you have that our wavelength is equal to 1 times 10 to the minus 6. And I know it was 1.1 times 10 to the minus 6, but we'll just do 1 times 10 to the minus 6 meters. You have a tool that says energy is equal to H divided by lambda. Do you remember seeing that? Or maybe you just had energy is equal to H times nu, which is the frequency. H is equal to Planck's constant, which is 6.626 times 10 to the minus 34. And it would, the units of that would be joules per meter. Do you remember this? Okay. And then what do we want? If I said what is the energy of that wavelength of light? So how much energy was actually contained within that wavelength? So another way you could ask that is how much energy did the electron have to absorb to jump from the third to the sixth? So energy is equal to Planck's constant, which is 6.626 times 10 to the minus 34 joules per meter divided by 1 times 10 to the minus 6 meters. Meters will these are not the right units. It's joules times meter. I gave you the wrong units for the constant. Sorry. Joules times meters, so now meters will cancel out, and we'll be left with just joules. And why is that nice for this equation?
How we measure energy.
It's how we measure energy. And so we get 6.626 times 10 to the minus 34 divided by 1 times 10 to the minus 6. And we get that our energy, and we'll keep it to one significant figure since this was in one significant figure, is equal to 7 times 10 to the minus 28 joules. And that's a really small amount of energy. That our energy is equal to 7 times 10 to the minus 28. Can you see this color okay? It's not great. I'll make sure I have a blue or black marker that works well the next time. So this is a really small amount of energy, but that's in a single photon of light. And so if you have, 1 times 10 to the 30 photons of light, you can have an enormous amount of energy being absorbed by these atoms and being released by the atoms when the electrons drop back down. All right? Any questions, thoughts, concerns? All make sense? Okay. Alrighty. Well, we are at our scheduled end time.